So we started talking about system thinking and what is system thinking. And so it's a lot different than, looking at processes in isolation. So we want to look at processes that are connected because the output of one process is the input to another process. And so when we look at a system, we talk about complexity. So I have these two systems up here, system A and system B, and which one do you think is more complex? Anybody?
The A is more complex.
Okay, that's actually correct. So why is system A more complex?
There's
Because
no
when we look at it
defined
from,
path.
what's that?
Because there's no defined path.
Yep. So in physics, Dr. Goldratt developed theory of constraints. In physics, he said system complexity is defined by the degrees of freedom. So the degrees of freedom is how many points in a system do I need to touch to affect that system. So in system A, of course, there's no connection. So I need to touch all 4 points to affect this system. So there's 4 degrees of freedom. In system B, if I could find the right leverage point and I could change that one point, it changes the whole system. Okay, so from degrees of freedom, system B is much less complex. Okay, and we talked about a system. So a system is just an organized purposeful structure that consists of interdependent and interrelated processes. So interdependent means that this second process here is dependent on the first process. So I can't do my work in process B here unless process A completes their work. That's an interdependency. We also have interrelationships where actions in one department can cause positive or negative effects in another department. And so we want to be aware of both the interrelations and interdependencies because that defines a system, and all organizations can be described as a system. So then what is leverage? Leverage is where we can apply a force, where we can apply a little bit of force and get big gains for it. So if we have, so Archimedes said if I had a lever and a leverage point and a lever big enough, I could move the earth. Okay. So there's, and it's also our ability to influence situations so so you can control what happens. So in system thinking, a leverage point is a point where we can apply some level of effort and get large gains. So I'm all about breakthrough improvement. So getting gains significant that people can't even believe it's possible. So more significant than what's the belief is possible. And then again, what we're looking for is that constraint in the organization. So what limits the organization from higher performance? If we could find that leverage point, improve that area, we see improvement for the whole organization. Okay, that's leverage. And then we talked about the different plant structures. So there's different plant structures. The first one we call the V plant. So a V plant, because of the configuration, it's like there's many divergent points. So you start out with few raw materials that go through divergent points, and as they go through the divergent points, the product changes, and then you offer a whole variety of products to the market. Okay, so that's the V configuration. So what we talked about is like plastic injection molders, right? They start with a resin, then they mold it into something, and then they might do some extra value added steps, and then they offer a whole variety of products to the market. And also, Steve Merson, right? They start out with carbon, right? It goes through different process steps, and then you offer a whole variety of products to the market. So powdered metal carbon companies would be V configuration. Okay, so few raw materials, once a path's chosen, you can't go back. So once you mold it into something, I can't go back very easily. Like plastic, you can regrind, but I don't know if like in powder metal, like once it's in the green state, it's hard to go back to the previous state. Okay, so a V plant is considered one-to-many configuration. So I have one component I can make into many different end items. Okay, so today's session, we're going to talk about the unique effects on these environments. So the unique effects in a V plant are stealing. So what does stealing mean? It means doesn't mean that people are taking materials home. But what happens is we steal when a product was supposed to go on a certain path, and then we steal that material to make a different product. So the material was allocated for one type of product, and then it's stolen and used for a different type of product or a different product that the customer might be screaming about or we're late on. And so we steal the material to allocate to another job. Okay, so why does divergent points result in stealing? Because we tend to maximize the performance of the departments to be efficient, and we pull orders ahead to enable to increase the batch size, or we group jobs together to have like materials and release them as a batch. And then to maximize performance, we produce the stock even though when there's no market request for the short or medium horizon. So I think we've had several examples in our weekly videos that we post about where people increase the batch size. I call it just in case. Oh, we have an order for 100, we'll make 125 just in case. So when we do that, we steal material from other jobs that we're allocating it to and overproduce on the job that we're running. Anybody do that in their plant? So Steve's like, yeah, we do that. So we got to ask ourselves, why are we doing that? Okay, so that's the V plant. So Steve, you should be able to relate to a lot of these issues, right? Because you're of the configuration. So the concept is there's certain unique characteristics of certain plant types, and then there's shared problems across plant types. But the stealing is a unique effect in a V plant. So what are the negative implications of stealing? So that typically there's high variability in lead time. So you could have stuff that has short lead time, which might be a few days, and then you have stuff that has a super long lead time that might be weeks or months. And it's all dependent on material availability. And then if we steal material, if we have a hard time getting material, especially today in the supply chain issues, we have a hard time getting material, and then we steal that material to produce for the medium or long horizon, then we don't have material for the short horizon products. So some stuff we might have in stock, so when the customer orders, it's like, oh, we can ship that in 2 days, and then other stuff that we got to produce, it's months to get that through the shop. So that's where we see high variability in lead time. Then typically due date performance suffers as a result of that. So when you have high variability in lead time, your due date performance usually suffers as a result. High levels of inventory, both in finished goods. I mean, if you make the stock in finished goods, if you're not make the stock, you make the orders, high inventories in production, and typically high inventories in raw material. So what happens is when you get shorted in raw material, then the purchasing people overreact and say, well, I'm not going to get caught short of material, so I'm going to over purchase. So then we have high levels of raw material and also high levels of work in process. So that results in too much of the wrong materials, not enough of the correct materials. And then expediting starts. So we have high level of expediting. So we break jobs in the middle to change over to the hotter job. So people come out and say, oh, stop working on that. We need this one. This is a new hot job. Work on this one. Then we have expedited freight to bring in more materials quickly. We run overtime to address late orders and inventory piles. And those are the characteristics of a V plant. Okay. The next one is an A plant. So this is having assemblies or convergent points. So remember the V plant was divergent points. This is convergent points where things have to come together. So typically there's lots of raw materials. So we have all these different components that go through convergent points into sub-assemblies, and we end up with a final product. So when I worked at GE making a locomotive, they're A plant, right? So they have 200,000 components that go into a locomotive, and you end up with a locomotive that you offer to the market. Boeing would be an A plant. So maybe what Dresser or Siemens is now, right? You're probably an A plant.
Yeah, it would be a plant.
So they have many components that go through different process steps and then end up with a a big unit that they ship to the customer. So different parts are needed for the same assembly and often produced by the same production departments, starting with many raw materials, going through conversion points, and ending up with few end products. So this is a many to one configuration. So you have one component that goes in many assemblies. So unique problem in a plant is poor synchronization. So if I go to assembly and I need 10 units to assemble that unit, 10 components to assemble that unit, I only have 9, I can't put the unit together. So the sequence, what's that?
Now think if you're getting 10 components to assemble a unit from all over the world too. So that'd be even more difficult.
So you see, the more variability, the more difficult it is. So Marcus is living that.
Every day, Max.
And so local efficiencies stand in the way of achieving reasonable synchronization, because it's like, why would I set up that machine to do one part? Right? It's like, I want to set up that machine and run as many parts as possible. So it's like, oh, I got 6 assemblies coming up, so I'm going to run 6 parts. So those 6 assemblies might be over the next several months. And then it's like, it doesn't make sense to set up to do one. Why would I do that? Right. So it's like departments are trying to maximize their efficiency in their department, and that causes the missynchronization, we call it. So the common effects in an A plant are stealing or cannibalism. So it's like, oh, we got this unit here that's partially assembled, and then this unit's only missing one component, so I'll steal that part off of this assembly and put it on this assembly so I can ship it, right? I cannibalize the jobs. And then that becomes a problem. So I'm actually working with a plant that's pharmaceutical, supplies pharmaceutical companies, and it's like material traceability and lot traceability is extremely important. So when you steal stuff, it causes major issues for the documentation and the information that's got to go with that unit. I don't know how much documentation you guys have, Marcus, but if you, and traceability, but
Yeah, we deal with the same thing a lot with like parts going scrap too. So then we're pulling up from other jobs to, you know, fill the current need, which I mean, I don't really see anything else we could do there. But the hard part for us is we used to be able to make everything, so you could just make something new, right? But now we order everything and buy out a lot of our products. So that's the hard part when it comes to that.
yeah, so now you lose control and you have more variability in the system. It's even more difficult.
Yeah.
I'm interested in the reason why you did that, because the parts are cheaper outside.
Everything's cheaper outside. Yep. That's it though. I mean, that's we buy from India and China, and
we'll talk about that when we get into the cost discussions.
Yep.
Oh, what is cheaper?
Right. I'm looking forward to that one.
Yeah, so talk about cheaper. So I actually talked to a guy, and he was working with Boeing, and so they had the capability to make some stuff, but then they decided to outsource it because it's cheaper. And because their schedule was so erratic, the supplier was up. They're always telling the supplier to change what they're making. It's like, oh, stop working on that. Oh, we need this order, right? And so, you know what their freight expense was just for that one supplier? $7 million.
Wow.
For expedited freight. It's like, how is that cheaper?
That's a lot of money.
Yeah. So it was just the one supplier that they had expedited freight over $7 million. Crazy. Okay, so what's the implications of poor synchronization? High inventories of finished components and assembly. So I have a bunch of jobs that are close to being finished but aren't quite finished. So usually there's, and I've seen that, I think I told the story about a ceramic company that makes glass furnaces. So a glass furnace, they make blocks out of ceramic. A glass furnace might have 75 blocks to it. And so when I go walk the plant, there's like all these blocks in the plant being worked on. And I'm like, so how are the people measured in the plant? They're like, oh, we're measured by how many tons per hour you can produce through your workstation. And it's like, okay, assemblies are made of big blocks and small blocks. So if I'm measured by tons per hour, which ones do I work on? All the big blocks. So I already know before I walk into assembly what I'm going to see. I'm going to see a bunch of orders with all the big blocks and missing all the small blocks. So sure enough, I go out in assembly and it's like all these jobs waiting for all the small blocks. So I got like 15 jobs partially done, all waiting for the small blocks, right? So that's the high inventories of, it might not be finished components, but in assembly, we have a bunch of jobs waiting to be completed and they're missing a few items. Okay, so many started but can't be finished, long lead times, missed due dates, orders are promised to the customer, then re-promised multiple times. You don't do that, right, Marcus? So it's like, oh, here's
No.
our first promise date, and it's like, oh, we're gonna miss that, so we're gonna re-promise it, and then, oh, we're gonna miss that.
Not once we actually have the order, no.
What's that?
Not once we actually have the order, no, but we do these things called pre-releases, and
Okay.
that's kind of contingent on when we receive the PO from them, but we're already starting work.
Okay. Then
But no.
Then priorities are constantly changing for upstream departments from assembly. They're breaking jobs in the middle again to change over to the missing component. High level of expediting, stealing components from spare parts inventory. So sometimes when we have spare parts inventory, we're stealing those to get the job shipped. And those are the A plant configuration problems. Okay, next is a T structure. And again, the A structure is a many-to-one relationship. A T structure is a many-to-many relationship. So we have typically almost every manufactured part is required by more than one assembly, and then almost every assembly requires more than one manufactured part. So when I worked at Cummins, they were a T plant. So they have a dedicated line for making blocks, dedicated line for making heads, dedicated line for making cranks, dedicated line for making cams, and each cam might be slightly different. Typically the blocks and heads are the same, but then in assembly, I can configure to the customer's order. So I have, they had like 6,000 different turbocharger options. Right, so I got all these configurable options I can do in assembly, but the main components, the block, the head, the crankshaft, the cam are typically the same or slightly different, right? They might have a block that has different boring for a different sub-assembly that might attach to it. Okay. So this is a many-to-many configuration. So I have many components that you can configure in many different ways. So the unique effects of a T plant, they have both the effects of a plant and a V plant. So the stealing and usually really poor due date performance, high inventories of finished components in assembly. Multiple assemblies can jump priority, so orders taken later ship earlier than orders taken earlier and vice versa. And that doesn't make the customer very happy when it's the same customer. They order all these components and it's like, wait, I ordered this one in middle of February and I got it already, but the one I did in January I haven't got yet. Where's that order? So it's lots of synchronization issues in the final assembly. So extremely high inventories, especially in component inventory due to unbalanced capacity of the production line. So I might have, limited blocks, but way too many cranks and cams. Okay, high level of purchase inventory and assembly due to configuration options, high level of expediting, breaking jobs to run the hotter job again, expedited freight, considerable lost sales because of the lack of synchronization, and then pressure to reduce the high level of configurations. Like we got too many products, reduce the number of products we have. Okay, so that's a T plant. And then the last one is an I plant. So this is an assembly line or a straight line flow where we don't have convergent points, we don't have divergent points. It's one process to the next, and typically they're tied closely together. So all products flow through the same sequence typically to make the finished product. There's a number of similar number of raw materials, work in process, and finished goods. And then it's a one-to-one configuration. So Nick, their business is electro polishing, and did you guys do any plating, or is it mostly?
Well, it's electric polishing and passivation.
So they have more of an I configuration, right? Each part goes pretty much through the same steps. There might be different lines. But
yeah, it's a multi-eye.
What's that?
It's a multi-eye.
But once it goes in that, right, it might go into tank 1, then tank 2, then tank 3, tank 4. If it gets stuck in tank 4, right, the whole line stops. Right? So the unique effects of an eye plant are small disturbances called starvation upstream and downstream. So if I have a step that takes longer, then I can't move the stuff in the previous steps, and the stuff downstream gets starved and the upstream gets blocked. And then overall equipment effectiveness is typically not good because all these disruptions reduce the overall equipment effectiveness. So if you're not familiar with the OEE concept, overall equipment effectiveness, it's 3 factors: the efficiency times the utilization times the quality. So efficiency is the actual output of the line compared to the design line output. So if I have a line that's designed that I can do 100 units per hour, and the first hour I get 90 units, my efficiency is 90%. So I get 90 units out of the line when it was designed to get 100. Then the second factor is utilization. So that's the uptime of the line compared to the total available time. So if it's available 10 hours during the day and I run 5 of those 10 hours, I'm 50% utilized. And then those 5 hours I ran, right, I was supposed to get 500 parts. If I only got 400 parts in that 5 hours, I'm 80% efficient. So I got a 50% utilization, 80% efficiency. And then the third is the first time quality. So how many came off the line first time right compared to the total units off the line? So overall equipment effectiveness is you multiply the efficiency times the utilization times the quality. Now, a lot of companies that aren't eye plants measure overall equipment effectiveness everywhere, and that's part of the reason we get missynchronization. We want to measure OEE on the constraint only. We don't need to measure OEE on every process, because by design, when we try to get synchronization, we want to have protective capacity in most operations. So the goal isn't to keep all operations busy. The goal is to have available protective capacity so that we can utilize that equipment when we have demand for it. We don't want to overutilize the equipment. Okay, so negative implications of an eye plant: poor due date performance, excessive overtime to meet customer demand, high pressure to keep the line running, minor stoppages reduce the utilization of the line. They put in Band-Aid solutions instead of fixing the maintenance. So taking the line down and doing the proper maintenance. So we put Band-Aid solutions in place. There's no time to do preventive maintenance. Quality issues move down the line. So it's like, don't pull the quality stuff out, move it down the line and quarantine it at the end. And then there's gaps in the line that reduce efficiency of the line. And then there's excessive effort to rework the product that is quarantined. There's poor relationships, finger pointing and blame, and pressure to run the line faster than it's designed. So I actually worked with a brewery that had a canning line. They were an eye plant and they had all these issues. And I actually went and visited a company that makes golf carts. And so they'd run the golf cart down the line. It's like, oh, we're missing a component, so just build them without that component. Then they have this whole parking lot full of golf carts missing the one item. When the one item comes in, it's like, oh, let's go do rework on all those carts so we can get those. And we saw it with the automotive, right? With the chips. What are companies doing? Making the cars without the chips. So let's make a parking lot full of cars that have no chips. And then when the chips come in, we'll put the chips in so we can sell the vehicle. So car assembly lines, actually, like Cummins, they have an assembly line, right? That's the assembly line is an I configuration. Anybody like Harley Davidson assembly line, so motorcycle assembly, anything that's done on a line configuration. Questions on that? And so then last time we also talked about the different plant configurations and different order types. So I got these 4 plant configurations, V, A, T, and I. I have 4 order types: make to stock, make to order, configure to order, engineer to order. So when you take those environments, you can put them into the 16 box matrix. So my belief is that every company can be categorized into one of those 16 boxes. So there's 16 unique configurations. So when I go into a company and said, oh, you don't understand, we're different. Yes, you're different only into this matrix, right? I haven't seen anything that's outside this matrix of 16 generic environments. And then again, each environment has their unique problems, and some environments have shared problems. So an engineer to order, right? I got usually a lot of engineering effort, and there's typically a lot of disruptions because we don't get all the specs from the customer correctly. And then when we start engineering it, there's stuff missing, right? And then we go back and re-engineer, and we spend a lot of time in engineering. Then they take a lot of the lead time, and then they throw it over the wall to production and say, good luck, right? It's like, we had a 10-week lead time. We took 8 in engineering. So manufacturing, you got 2 weeks to get it done. Where make the stock, we don't have engineering, right? So typically, we're trying to hold finished goods inventory and ship from finished goods. And then the only other variable is how much mix there is. So this is product mix in terms of how much variability in product mix do we offer. Okay, so the higher variability in mix, the more difficult to get synchronization. Okay, then there can be combinations of plants. So V base with a T top, A base with a T top, B base with an A top. So there's all different configurations. And if we have a combination of these, then we have multiple effects that we see based on those plant types. Questions? That's sort of our session for today. Anybody relate to those issues we talked about? So what's the cause of those issues? So my contention is most of the causes are because of lack of synchronization, trying to be efficient everywhere. So we could go back to our rowing concept. Because a lot of times I see companies create artificial bottlenecks because it's like, oh, this is the most efficient line to run it down. So we got to run everything across that line. And then we get a huge bottleneck, and then we can't get the work through, and then all the trouble starts.
Yeah, I mean, I may lose a little bit in my run rate. I may lose a little bit in my efficiency, but ultimately I'm hitting my due dates ahead of time and clearing up my schedule, right?
Exactly right. That's the exact right thing to do.
Okay.
And opening that capacity for, right? Because now when a new order comes in, if I have that open capacity, man, I can turn it quick. And it's again, what's the needs of your customer? So I assume that when they bring it in, they want it turned as fast as possible, right? They don't want it sitting in your shop for weeks.
Yeah, I mean, we get 3 to 5 days in most cases to just turn things around. So we have to kind of use every gap we have.
Yep, exactly right. Okay, so we talk about synchronous flow, we talk about effectiveness versus efficiency. So what's the difference between the two? And I like to use a rowing crew. So our goal is to flow work to customer demand, just sort of like what Nick was talking about. And so when I have these two rowing crews, right, this first rowing crew is very effective, right? They're rowing in sync, everyone's rowing to the same pace, and the boat's going straight line to get to the finish line in the most effective manner. The second rowing crew here, I got this second rower who's 3 times more efficient than the rest of the people. So what happens when he's 3 times more efficient? The boat goes off course. So what happens is if we have everybody in the company trying to maximize their own efficiency, it drives the company off course. And we have unbalanced capacity. So that means we have different capacities in different departments. Trying to keep everyone busy and efficient is what's causing the missynchronization. The missynchronization is causing all the issues that we saw in the plant configurations, which is a hard concept. It's easy concept to understand, right? It's extremely hard to implement because people are so caught up in like, I need to be efficient in my department. I need to be efficient, need to be efficient. No, sometimes by you being less efficient actually helps the company. So if anybody's ever played the dice game, that's what the dice game proves. It's like by being less efficient, we actually get better system performance. But that's a whole mind shift change. And it's like, we got to have leadership buy-in. It's like, hey, we're going to have people standing around with nothing to do from time to time. It's like, what? So by design, I like to have at least 20% protective capacity in all areas except the constraint, right? So if we have a constraint, everyone else has 20% protective capacity minimum. That's now the more variability we have in the system, the more protective capacity we need. So if we have high variability in cycle times, high variability in mix, so remember that chart I was showing the variability. So all that means is here, the more variability, the higher the variability in mix, the more protective capacity we need. So some cases you might need 50% protective capacity. So what does that mean? It means on a 5-day work week, we're only planning to utilize those resources 2.5 days. In a normal design with not a lot of variation, it's a 20% minimum. So that means most steps in the process are only designed to work 4 out of the 5 days. Why is that important? Because we need time to overcome problems. We're still going to have problems. Machines are going to break down. People aren't going to show up for work. We're going to have suppliers deliver late. We're going to have suppliers deliver poor quality. We're going to make quality issues ourselves. So we got to have that protective capacity to overcome the disruptions. If you don't, the disruptions will drive all the way through your system to the customer. So a delay in one department will cause late shipments to the customer weeks later. So we need the ability to, I call it sprint, to catch up when we have a disruption. Because we can't fix all the problems, right? So how we get stability immediately is like stop people from working, focus on flow, and then when we have disruptions, figure out how to overcome that disruption as fast as possible to keep flow going. And that's the flexing of the resources that Nick was talking about, moving it to a less effective line if needed, right? We have variability in demand coming in. So it's all about managing variability in the system perspective.